Hello everyone, I'm Prarthana. Today I'm going to present on memory management in operating system. Memory is one of the most important resource in a computer. It directly impacts speed, efficiency and multitasking ability. Without proper memory management, even the most powerful system will slow down or crash. So let's explore how an OS manages memory efficiently. First, introduction to memory management. It is the process of controlling and coordinating computer memory. The OS ensures that different programs get the memory they need while preventing issues like memory wastage and leaks. For example, when we are opening multiple apps on a mobile phone, the OS allocates memory to each app dynamically. If memory is mismanaged, a phone may be start lagging or even freeze. So memory management is essential for smooth computing. Next, memory hierarchy. Computer system is organized in a hierarchy from fastest to slowest. First, registers. Small, ultra fast memory inside the CPU. Next, cache memory. Slightly slower than registers but stores frequently accessed data. Main memory. The primary memory used for running programs is main memory, that is RAM. Secondary storage. It is permanent storage for files and applications. Examples hard disks and SSDs. Next, virtual memory. It is used for extending RAM when we need page file and swap space. For example, when our laptop runs out of the RAM, the OS uses part of the hard disk as virtual memory, which slows down performance but keeps the system running. Next, memory allocation. Memory allocation is done in two ways: contiguous allocation and non-contiguous allocation. Contiguous allocation is the memory blocks are assigned in a single continuous space. Non-contiguous allocation memory is assigned in scattered blocks to maximize usage. Also, memory allocation can be static allocation and dynamic allocation. In static allocation, memory is assigned before execution. Example, global variables used in C. And in dynamic allocation, memory is assigned during execution, like malloc used in C program. A good example is how our browser allocates memory dynamically when opening multiple tabs. Next, let's see brief explanation for contiguous memory allocation. There are two types of contiguous memory allocations: fixed partitioning and dynamic partitioning. Fixed partitioning. Fixed partitioning divides the memory into fixed size partitions. In dynamic partitions are allocated as per the process requirements. The issue with contiguous allocation is external fragmentation, where free memory is scattered across the system, but the usual due to gaps between occupied memory blocks. Next, non-contiguous memory allocation, paging and segmentation. To overcome fragmentation, we use non-contiguous allocation technique like paging and segmentation. In paging, the OS divides memory into fixed size pages and assigns them to frame in physical memory. Segmentation, memory is divided into logical segments like code, data, and stack rather than the fixed size. For example, paging is used in modern OS like Windows and Linux to efficiently manage memory without fragmentation. Next, virtual memory. Virtual memory allows a computer to run programs larger than its actual RAM. It achieves this by storing part of programs on the hard disk and swapping them into RAM when needed. For example, when we are run multiple heavy apps, our OS automatically moves inactive parts of the page file on disk, freeing RAM for active tasks. However, using virtual memory is slower than the real RAM. Next, page replacement algorithms. When memory is full, the OS must replace pages to load new data. Popular page replacement algorithm includes first in, first out. It removes the oldest page. LRU, least recently used. It removes the least recently accessed page. Optimal page replacement. It predicts and removes the page that will not be needed for longest time. For example, modern browsers use LRU when managing multiple open tabs. It lets user tabs are offloaded first to free up memory. Next, demand paging. In demand paging, pages are loaded into memory only when needed rather than preloading everything. If a record page is missing from RAM, a page fault occurs and the OS fetches it from virtual memory. For example, when opening an image heavy website, only visible portions load first and remaining images load when we scroll. Next, thrashing. Thrashing happens when the CPU spends more time in swapping pages in and out of memory rather than executing the processes. This reduces the performance of the computer. Solutions for thrashing may include increasing RAM, optimizing running process, using the working set model to limit active processes. For example, if we have too many apps open on a low RAM phone, it may lag due to excessive swapping. Next, memory fragmentation. Memory fragmentation occurs when free memory is divided into small unusable chunks. There are two types: internal fragmentation and external fragmentation. In internal fragmentation, unused memory inside allocated space. In external fragmentation, scattered free memory blocks are there. For solution, they use compaction and paging. Compaction means rearranging memory to group free space together. Paging means eliminates fragmentation by allocating fixed size blocks. Next is swapping. Swapping moves process in and out of memory to optimize space. For example, in multitasking OS, if one app is idle, the OS swaps its to virtual memory to free RAM for active application. Next, memory protection. Memory protection prevents unauthorized access. The memory management unit ensures that one process cannot access another process memory, preventing crashes and data leaks. Next, shared memory. Shared memory allows multiple processes to access the same memory space. It improves efficiency. This is widely used in inter-process communication for data exchange. Next, cache memory. Cache memory is high-speed storage that holds frequently accessed data to reduce CPU's waiting time. There are three types of cache mapping: direct mapping, associative mapping, set associative mapping. For example, processes use cache memory to store frequently used instructions and boosting performance. Next, translation look aside buffer TLB. TLB is a small fast cache that stores page table entries to speed up address translation in visual memory systems. Next, memory management in different OSs. Different OSs use different memory management strategies. Windows uses paging and segmentation. Linux uses demand paging and swap spaces. Mac OS uses hybrid memory approach with compression for better efficiency. Future trends in memory management includes AI-driven memory optimization, automatically predicting memory needs, quantum computing, revolutionizing data storage, high-speed non-volatile memory, faster and more reliable memory technologies. Next, we are at the end. Summary and conclusion. To summarize, we covered memory allocation, fragmentation, swapping and virtual memory, paging replacement and security, future trends in memory management. Proper memory management is crucial for system performance. Thank you.